Hello and welcome, my fellow chem mortals. We're going to go over the chemistry solver program available at mcstutoring.com. Of course, you already know, links in the comments. So we're going to go over kinetics today. So let's go option 7. I just want to show you the basics. We've got the rate law at first, so we can solve for any of the missing variables there. Then we also have the Arrhenius equation, and again, solve for any missing variable there. And then reaction half-life. I forgot the E here, but forgive me. Solve for T sub half, like the half-life time. Solve for K. And I want to show you a view intro because there's a half-life, there's a nuclear half-life versus chemical half-life. Chemical varies with temperature. See the Arrhenius equation, and nuclear, it's a constant half-life. So see nuclear chemistry section. So without further ado, let's get back to this rate law here. We're going to do problem number 1. Let's get started. So we got the calculate the reaction rate for H2 plus I2 yields 2HI. That's hydrogen, I think iodine, or iodine, depending where you live in the English-speaking world. Okay, so what we're going to do, calculate the reaction rate. So that's going to solve for the rate here. And then what's the rate constant? K is 2 times 10 raised to the -2. And remember, use that negative sign right here, just to the left of the answer key here. If you use the minus, ooh, bad news, calculator will not work too well with that. Okay, and what is the A, like the molarity for the A part? And we're going to call this the A, and then this thing the B. So the molarity is 0.04, is it 0.04 moles here? I'll circle reaction rate because that's what we're looking for. Okay, and what's the order? If they don't give the order, we're just going to assume the order is 1. I don't go too far into that here, and you probably won't see that in a basic or like intro chemistry class. Okay, the molarity for element B, that's going to be 0.035, so 0.035 we enter right there. And then what's Q? The order is 1. If it does give the order, we're just going to assume 1. And then the rate is 2.8 times 10 to the -5th. So just so you know, those people unfamiliar, when you see this in a calculator, 2.8 e to the -5, that's 2.8 times 10 to the -5. That's how calculators, or at least the TI-84, renders scientific notation problems. And then again, you are going to have to memorize the units. That's going to be meters per second. Or sorry, what am I talking about? Moles per second. Oh, goodness gracious me. Okay. Now, determine the rate constant, which is K, for 2 NO plus O2 yields 2 NO2. I think we're talking about nitrates here. So what we're given, or actually, sorry, we're solving for the constant K, the rate constant, and then the rate itself is 3.6. That's going to have to be given to you guys, times, excuse me, 10 raised to the -4. I think again, we use the symbol raised to the here above the division symbol. It's a caret. I don't want to get into it. Flame me in the comments if you think I'm wrong. The molarity for the first thing is 0.06. And then the order for that, now make sure it's, okay, we've got the molarity for NO, and the order for NO is 2. Okay, so this is one case where it's not always 1. Okay, and the molarity for the second thing, or the is 0.025, that's for the O2. And then the Q, the order for that is 1. Okay. If you're wondering where we're getting that from, by the way, it's the coefficients. I'll highlight those for the unfamiliar. If you're already familiar, you go ahead and fast forward. So they get this 2 as the coefficient here, and that's 2 as the coefficient there, just so you know how we're getting everything. Okay. We go on, and then, oh, the rate is 4, and we're going to assume it's 4, and that's m to the -3, s to the -1. So that would look like this, 4m cubed s, 4 over m cubed s, if you write it with positive exponents there. Okay, cool. I was going to say coefficients. My goodness. My math brain, where is it? Okay. Find the concentration of O2, and NO plus O2 yields NO2. So we're trying to find the concentration. So we're going to go for the molarity, I believe. Okay, and what's the rate? It's 5.4 times 10 raised to the -4. And then what's the K? What's the rate constant? Okay, that's 1.8 times 10 raised to the negative third. So that's that number. I got that number from. And then what is the molarity for item B? Well, we're going to call that B here. 0.15. I might have changed the order, but as long as we're consistent throughout, we're going to be okay. The order for it is 1. And the order for the other thing, the original thing, the M, or the molarity for the, the order of the power for it is 1. Okay, and then we get 2, and again, that's 2 molar as our answer. Okay, good, good. Now, Arrhenius equation problems. Yes, good. So we're going to go back, and then we're going to go to Arrhenius equations. And then calculate the rate constant at 300K. So we're going to solve for the rate constant, by the way, is small k. So that's this option here, the first thing. So we can do that. Oop, yep. And then we get A. What's A? 2 times 10 raised to the 10th power. And then E sub A, meaning the activation energy activation. That's E supposed to be sub A. It would look like this if I had my druthers. Texas Instruments, if you're listening. Okay, and watch this. I like this. Okay, whoa. I don't like these crazy numbers here. Well, look, this 75 kilojoules, typical chemistry question devilry here. This is 75 kilojoules. So it's like 75,000 joules per mole, okay? I just want you to know that. So that's 75,000. It's like 75 times 10 to the third, because that's kilojoules, but we want it in joules per mole. So just be mindful of that. You could have all the right formulas and equations, but if you don't see, it's like, oh, the units, it's supposed to be just regular joules rather than I've given kilojoules. So just be mindful of that. That's where a lot of mistakes are going to be made using this program. Okay, and then temperature is 300K, temperature in kelvins. So we're going to go 300. And then we get 0.00174. So that would be 1.75 because we move the decimal 1, 2, 3 to the right. So that would be 10 to the negative third. So 1.75 times 10 to the negative third. And then units is like per second. So it would be like blah, 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 the number, and then second as the denominator. Okay. I just realized I got to change the nib on this stylus. Oh my gosh. Okay, now we're going to solve for activation energy. That's option 2 here. Energy of activation. Okay, what is the K? The K is the rate constant. So it's, 4.5 times 10 raised to the, and you get that negative thing going on, negative 3 versus minus 3. So we're going to use that negative symbol below the 3 key. And what is the A? Okay, it's going to be 3 times 10 raised to the 9th. Good. And what's the temperature? It's 325 because it varies with temperature. Okay, and we get 31948.79. We're cool. And that's joules per mole. If your teacher's like, hey, I want you to write it in kilojoules, you know, move the decimal over 3. I'll show you what that looks like. It's like 1, 2, 3. So that's how you get that answer. Okay, good. Now we're on to chemical half-life problems. And again, just so you're like, hey, reaction half-life, what is, and I put in view info because I was confused myself. I'm like, hey, you know, I'm not really a science person coming to this. I'm more a math person. So I'm going to view the info. And it shows chemical half-life versus nuclear half-life. Chemical varies with temperature. That's why varies the temperature. See the Arrhenius equation. Nuclear constant. Nuclear half-life is constant. See nuclear chemistry section. Okay, enough of jaw jacking. We go on. So we're going to, in this case, solve for the half-life, the T sub half. So it look like this, T half-life. Time and half-life. K is 2.5 times 10 raised to the negative 2. And then we get 27.7. Now notice this is in seconds. I could totally see a professor, teacher, instructor, whoever's writing your exams or quizzes or tests. They're going to say, what is it in days or hours or minutes? So you got to do the conversion right from seconds to minutes or what have you, or back to seconds. So just so you know. Okay, we're going to now solve for K, the rate constant from the half-life data. Yeah, it's dependent on K, not the temperature. The K is the half-life constant. I'm sorry. So look, flame me in the comments. I realize now I made a mistake. I'm not going to remake this video. You guys are going to have to live with it. Sorry about that. So the half-life in seconds is 45 for this guy. So, and it gives you the formula, which is great. K is ln2 over t sub half. So K is 1.54 times 10 to the negative 2 per seconds. Okay, good. So look, if you like it, like it. If you want to see more stuff like this, subscribe, obviously. I know everybody is like, hey, please like, please subscribe. Hey, it's cool. If you like it, like it. If you don't. That's fine. But if you do have a comment, put it in. I'll change this program or modify it. And gosh, I made this big gaffe. So look, everybody who listened to this in its entirety, I realize I made that gaffe with the K, with the temperature or whatever, originally with the view info. It doesn't, I don't think it varies with K. I think it varies with the rate constant, but whatever. Okay, I could be wrong. Go ahead, put in the comments. If you're a chemistry person, you get to roast me. Okay, I look forward to it. And good luck in all of your chemistry and math and SAT endeavors. I'll check you next time.